Energy. Imagine your life without it. Everything depends on energy nowadays. Your mobile phone, your house, your city, and your world. Incredible amounts of energy are produced every day worldwide, using traditional methods like combustion of fossil fuels, or through more advanced, modern and sustainable technologies such as wind turbines and solar panels. Of course, there will be moments when there is more energy being generated than being used. With the old fossil fuel power plants, it's possible to put less fossil fuel in, but with modern technologies, which depend on the environment, it is not that easy. Imagine a sunny and windy day. Everyone is outside, so there is hardly any energy used in homes. On the other hand, wind turbines and solar panels are at their peak performance. As you can see, this leads to a problem and requires a solution: energy storage. We can all think of one way of storing energy: batteries. And indeed, they are a good way of storing energy. Think about your mobile phone and laptop. They both use batteries. Unfortunately though, they cannot be charged as fast as would be necessary in case of an energy excess. This lies in the functioning of the battery itself, mainly in the chemical reactions that take place inside of it. Capacitors are another way of storing energy and do that differently than batteries. They store their energy electrostatically, or, in other words, create a difference in charge. You could imagine this as rubbing a balloon against a wool cloth. By putting in work, you move negative particles, or electrons, from one object to the other. This creates a charge in the balloon, which is energy. This energy can later be released in the form of an electric discharge, which can be imagined as a spark. Now, imagine two pieces of metal instead of a balloon and a cloth. Put something in between that prevents them from touching each other, and finally replace the work you put in with a voltage source. You now have a capacitor. Basically, a capacitor consists of two parallel metal plates, called electrodes. They are physically separated from each other by an additional layer, called the dielectric, that can be made of specific materials, like plastic or simply air. This means that the plates are not directly connected and, as a consequence, there is no current flow between them. If you now apply a voltage on the electrodes, the electrons will start flowing and the capacitor will get the same difference in potential, creating energy and storing it between the two plates. If you remove the original voltage source, the capacitor will keep its charge. This means that if you connect another component that needs power, for example a light bulb or a motor, to the capacitor will discharge again, making the light go bright or the motor turn. The main disadvantage of such devices is the low energy density, especially compared to batteries. They can charge and discharge way faster, but the amount of energy that they can store with respect to their volume is really low. However, developments and discoveries in the land of capacitance brought to new ways of generating and storing energy in an electric field, which increased the energy density of these devices. The reached values were incredibly high compared to traditional capacitors, and for this reason they needed a fancy name: supercapacitors. In a supercapacitor, there is no dielectric between plates. Rather, there is an electrolyte and a thin insulator such as cardboard or paper. There exist three types of supercapacitors. The simplest one is the electrostatic double-layer capacitor, or EDLC in short. The EDLC resembles the classic capacitor the closest. The electrolyte contains positively charged particles and negatively charged particles, ions. When you apply a voltage on the electrodes, one of the electrodes gets positively charged and the other gets negatively charged. Because of electrostatic attraction, the negative ions get attracted to the positive electrode and vice versa. Now something special happens. As the ions touch the surface of the electrode, they form a very organized layer. You can imagine this as the full surface of the electrode being wrapped in a layer of ions, exactly one ion thick. Now the charge is stored in the very small distance between this layer and the electrode. This phenomenon is called the Helmholtz double layer. This means that the layer in between the electrodes can be made way thinner, which leads to EDLCs having a much higher energy density. However, compared to batteries, this is still quite low. The second type of capacitors are called pseudocapacitors. The difference between an EDLC and a pseudocapacitor lies in the way of storing energy. The first way is similar to EDLCs, A pseudocapacitor uses the double layer to force a layer of ions on the electrode to store a potential. In this case, the energy is stored electrostatically. The second type of energy storage involves the electron charge transfer between the electrode and the electrolyte. Specifically chosen materials allow the electrodes to host a very fast sequence of redox reactions that enable to store energy electrochemically. The last type of supercapacitor is the hybrid supercapacitor, also known as an asymmetric supercapacitor. It combines both the EDLC and pseudo-type. This means one of the electrodes stores energy electrostatically and the other one electrochemically. This combines the fast charge and discharge rates of the EDLC with the higher energy density of the pseudocapacitor. But why do we need supercapacitors? Aren't batteries sufficient? For some applications, batteries are the best solution. But, as already mentioned, when you want to charge or discharge rapidly, supercapacitors are the preferred option. Also, the cycle life of supercapacitors is much longer. A normal battery can handle 100 to 10,000 cycles before the battery dies, but a capacitor has a cycle life of more than 500,000 cycles. So supercapacitors could be a replacement for the battery in your mobile phone. You will never have to replace that battery anymore and it will charge much faster. In electric vehicles, supercapacitors could be used as well. Short charging times and fast release of energy, optimal for a quick acceleration. But why are these two examples not reality already? That is because of the low energy density compared to batteries. For a phone, you want to store as much energy as possible and thus require a large energy density. Unfortunately, this is not the case for supercapacitors, yet. Since pseudocapacitors have the highest energy density, it is most likely that researchers will try to find new materials that have the properties that are required to maintain the benefits of supercapacitors. Promising materials are transition metals like transition metal nitrate and transition metal oxides. I hope you enjoyed this video, learned about supercapacitors, and next time you hear something about them on the news, you will be able to understand why it is big news and see what their place in society could become. Thanks and bye bye.